Good morning. So we get to the last lesson of chapter 8, the so-called Bernoulli Trials, which is a very nice quick application. Well, quick in the sense that it will basically lead to yet one other formula. So an immediate application of the combinations that we learned before in the previous section. A very simple formula to set up, maybe not so simple to compute in some cases. It may be a little bit tedious, and it definitely requires in many cases the use of the calculator. But it's a simple formula to set up, and it's a very powerful one because it allows you to answer very, very useful questions you may have in real life situations, so to speak. But the formula is only specific to a certain kind of experiment that is performed repeatedly. Experiments with two outcomes, which we will define later on. So what we call Bernoulli trials are a very specific type of experiment that is repeated several times, 2 or more times, and each experiment has only 2 possible outcomes, which is the reason we start with an example to illustrate what we're talking about before we state the formula and some other applications. So take a moment. You're going to have to pause, obviously, the video at some point to catch up with what I wrote here. But take a moment to write down the example that I wrote already here, and also to sketch this branching tree, which I'll explain immediately what it means. Try to make a nice picture, leave enough room on the page so that you can have room to write the probabilities that you're going to have to write on each branch of this tree. So here is the example. Let's say we have a loaded coin, and I make it a loaded coin just to make the example as illustrative as possible, so that it's not, because if it's a fair coin, you know, the probabilities will be equal between the 2 outcomes. So it's a loaded coin that is tossed 3 times. So the experiment is tossing a coin, except that it's repeated 3 times. And the probability of a heads is 1/4, so it's not 1/2. It's 1/4 since it's loaded. And that of the tails obviously is going to be 3/4. So it's a loaded coin in which you have less chance to end up heads than tails, right? The probability of heads is 1/4, tails is 3/4. We're going to ask some questions on the outcomes of these experiments immediately. But for now, let's sketch a branching tree indicating all possible outcomes. So you don't have to do this unless the problem will ask you to do. But to illustrate what the issue is and why some powerful formulas are useful to answer questions based on these type of experiments, what I want to suggest here in this branching tree is all the possible outcomes that come from these 3 tosses, right? So you toss the coin 3 times, and then what are all the outcomes when you're done for all these 3 experiments that are basically, or for this experiment that is run 3 times. So you can think of the root of the tree as the first toss. So let's write it like that. This is the first toss, which obviously results in either heads and tails. And as you remember from a previous section, we can write the probabilities of each of these on the actual branch of the tree. So 1/4 for heads, 3/4 for tails. Now notice that for each possible outcomes in the first toss, you're going to have 2 possible outcomes when you move on to the third toss. So this is basically what you see here is the outcome. Well, I should put it, sorry about that. That's the root of the tree. This is the first toss, right? So the one that results in either heads or tails. Okay, now you have the second toss. But in the second toss, notice you have 4 possibilities because each of them can be combined with either heads or tails, right? So here we're going to have second toss. And obviously here on this last level, the third toss. All right, so on the second, after the first toss, when you move on to the second toss, if you had a heads in the first toss, again, the probability of the second toss is either heads or tails, each of them with the probability 1/4, 3/4. Or if you had tails prior to that, again, the outcome on the second toss could be heads or tails with probability 1/4, 3/4. When you move on to the third toss, obviously you have so many other combinations possible, right? Because you have 4 possible roots, right, in the second toss because of these combinations. So again, you can have heads and tails, 1/4, 3/4. So write down these probabilities on the branching tree. And then here are a couple of questions you can ask. So in the first question, let's say I ask, what is the probability that we obtained 3 heads in a row? So one thing to notice, and we should write it as a remark here, each toss is independent from the other. Now remember, when you compute the probability of the intersection of independent events, the formula states that you multiply the probabilities. And if the events are mutually exclusive and you have to compute the union of events, then you add the probabilities. But for the independence, the probability is the multiplication of the probability of each event if the events are independent. Let's put that as a remark here. Why that's important? Because each toss is independent from the other. So basically, to figure out the probability of one outcome is essentially, this leads to multiplying the probabilities of each individual outcome from each toss. So I want you to notice that to have 3 heads in a row, we have only one possible situation out of all these possible outcomes. So in fact, let's actually write down here in let me see if I can fit it here. I'm gonna try to put it here in a column right near the 3. I'm going to write down the outcomes possible, right? So if you're here in the first position on the tree, that means you had heads, heads, heads. I hope it's clear enough there. And then when you move on to the second possibility, that's heads, heads, tails. Here it's heads, tails, heads. HTT. Tail, heads, heads. Tail, heads, tail, 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 heads, and then tails, 3 tails in a row. Right, so in total you have essentially 1, 2, 3, 4, 5, 6, 7, 8 outcomes. Of these outcomes, of these 8 outcomes, only one of them satisfies the question, right, the requirement in the question, 3 heads in a row. And the probability of 3 heads in a row, again, it's like us saying the probability of heads first, heads second, heads third, but because the events are independent, the probability of 3 heads in a row is simply the product of the probability. 1/4 times 1/4 times 1/4. So because these are independent, when you actually compute the probability of one of these outcomes, that means you multiply the probabilities of each branch, right? Because again, each toss is independent from the other. For example, if you want the probability of heads first, tail second, that's going to be the probability of heads first, which is 1/4, followed by 3/4, the probability of tail second, and 3/4, the probability of tail third in the third toss. Let's actually compute these fractions. So 1/4 to the power 3, that's 64. And this would be 9/64. Okay, but here's a different type of question, and this is basically the one that leads to the formula that will require the combinations eventually. What if I ask, what is the probability of exactly 2 heads out of these 3 tosses? All right, so what makes the question is a little bit more complicated is that I don't actually indicate when these heads should come up. Is it the first or the second, the first or the third, the second or the third? So there are multiple possibilities for these two heads to appear. And the question is in such a way that that's not important, right? So I simply want to know if I toss a coin 3 times, what will be the probability that I will obtain exactly two heads? Now, if you use the tree of probability, we can just basically count the appearances of two heads. So you could have, if you look at look again on the tree here, you could have heads, heads, tails, or I could have heads, tail, heads, or I could have tail, tail, heads, heads. Now, or remember means union in the language of probability. And notice also that these are mutually exclusive, right? So these are distinct outcomes when you look at the tally of all possible outcomes from these three tosses. So when I compute the probability of this union, I just add the probabilities of all these three outcomes. Each of them again is obtained via multiplying the probabilities of each of these toss, right? So for heads, heads, tails, I have 1 over 4 times 1 over 4 times 3 over 4, to which I add 1 over 4 times 3 over 4 times 1 over 4, and then finally 3 over 4 tails times 1 over 4 times 1 over 4 for the two heads. And I want you to pay attention to this summation here and notice that first of all, each quantity is the same because we can interchange the order of the factors here, right? So you have basically 3 instances or 3 terms which contain 1 over 4 to the power 2. 1 over 4 seems to be multiplied twice, right? Because I have heads, heads. And 3 over 4 is to the power 1. Okay, so all of these terms have a very specific meaning when you actually write the formula in the general sense, right? We're not going to prove this in this class, but as it turns out, this coefficient here will be a combination. You will see that on the next page. And this 2 has to do with the statement that I want 2 heads. And of course, the remaining one has to be a tail, right? So, I mean, because you have 3 tosses in this experiment, okay, so I toss the coin 3 times, then the exponents will always add up to the number of times for the experiment is executed. Also, the number of times you execute the experiment, that's going to be in the formula, right? The summation of the exponents will be the number of times you run the experiment. So I'm anticipating basically the formula that it will contain combinations as a coefficient, and you're going to have these probabilities raised at these powers that will have a very precise meaning, namely the number of times one outcome you want to be realized. So why do we need a special formula to do this? Notice that if you rely on the tree, things can get pretty complicated and unfeasible rather quickly. What if I, for example, say, as a little motivation, what if I toss 10 times? What if I toss the coin 10 times and I ask, what's the probability of obtaining exactly 2 heads? Now, notice how big this tree is just for 3 tosses. If you're branching out further, the tree, for 10 tosses, you're not going to have room on the paper to do this full tree. Even if you don't do the tree, but also you just write the outcomes one by one, that's still extremely unfeasible, right, for big numbers. So that's the reason why we have a special formula for questions like this. So on the next page, I'm going to define in a more rigorous manner what a Bernoulli trial is. This is what you see here, an example of a Bernoulli trial. And the formula for the probability of the Bernoulli trials, and then finally a couple of applications to finish the lesson. So stay tuned. All right, so let's read together this definition. You're gonna pause the video after that to make sure you write it down, and then I'm gonna comment to make sure we understand each word, what is all about in this definition, so we can recognize in problems when we deal with a Bernoulli trial. And then we're gonna write down the formula for the probability of a Bernoulli trial. So a Bernoulli trial is simply a name for a specific type of experiment which is run several times. But there are some conditions to be met, okay? So again, flipping the coin repeatedly is the best example to keep in mind as the default framework for the Bernoulli trial. So you have a random experiment, and to be called the Bernoulli trial, the same experiment is repeated 2 or more times. So, I mean, without this condition, there's no point in talking about anything special. Right? So you have an experiment that is repeated 2 or more times. Another crucial condition is that there are only 2 possible outcomes. Because there are only 2 possible outcomes, and because in these applications, you typically are looking for a certain outcome to come up, for convenience, we're going to call one outcome success and the other outcome failure. Sometimes people are confused in the beginning of these wording, because usually the word success is associated with a positive feeling and failure with a negative one. But you got to basically think in general statements. Like, for example, if I want to know, as you will see in an example later, you know, how many, for example, of the, you know, cases of the next, for instance, cases of lung cancer, how many of them were smokers, for instance, you know, so there, in that case, you could think in terms of success being the smoker, basically, because you're looking for two outcomes, smoker or non-smoker, and then you run that experiment, and then, you know, you're looking for a specific probability associated with a precise number of smokers in the next group of, for example, of people with lung cancer. So success doesn't mean good necessarily. So it's not like we attach an emotion to these words. It's just a convention from a mathematical standpoint, so we can formulate the formula easily to call one of the outcomes success and the other one failure. For example, in the previous example, because I asked about obtaining a certain number of heads when I tossed the coin repeatedly, then in that case, heads was called success. And then tails obviously is failure. But if I wanted to figure out, for example, the number of tails out of I don't know how many tosses, then of course you could call tail the outcome to be success. So it doesn't really matter. There's just, the important thing is that there are only 2 possible outcomes, one called success and one failure. Another crucial requirement, of course, is that the trials are independent. Otherwise the formula doesn't work, right? And the probability of each outcome remains the same for each trial. So nothing changes, right? The experiment is the same, run independently 2 or more times. Okay, so once we recognize that we have a Bernoulli trial type of experiment, then the formula that is useful in this context, and let's write it here, the formula, which is also given the formula sheet, by the way. So the formula for Bernoulli trial and that formula will answer basically a very specific question. So in a Bernoulli trial, the probability, actually I jumped ahead a little bit. So let's say we have a Bernoulli trial in which the probability of success is P, and obviously the probability of failure, you should basically know what the answer is. Maybe you should pause for a moment. I said there are only 2 outcomes, so if I call the probability of success is P, then you should realize that the probability of failure is 1 minus P, right? It's because the 2 have to add up to 1. So in a Bernoulli, so let's say we have a Bernoulli trial, right, with the probability of success being P and the probability of failure 1 minus P. In a Bernoulli trial, and now we came to the formula, the probability of exactly, pay attention to these words, of exactly K successes in N trials is, and the notation is B of N comma K semicolon P. That's the notation for the probability of K successes out of N trials, is equal to the combination of N choose K times P to the power K times 1 minus P to the power N minus K. In the book, I think in some books they call the probability of failure Q, but remember, since there are two outcomes, they should add up to 1. So I'd like to just state the formula like that. So in the previous example, and we're going to do more examples obviously before we call it a day, N was 3. So again, let's make sure we understand the meaning of each terms. Lots of mistakes happen from confusing the role of these terms. So make sure you know very well or very clearly what each of these numbers stands for. So in this notation, because there could be various notations in other books, but in this notation, N denotes the number of trials, the number of times you repeat the experiment. K represents the number of successes you're looking for. So if you're asking, for example, I want to know if I obtain 3 tails or 3 heads out of 7 trials, then K will be 3, right? The number of successes. After semicolon, we're going to put the number that represents the probability of success, which is denoted by P in the formula. So in the previous example, because I tossed the coin 3 times, N was equal to 3. Because I asked whether the probability of heads 2 in a row, I mean, what's the probability of obtaining 2 heads out of 3 trials? K was equal to 2. And because it was loaded coin, remember the probability of heads was 1 over 4. So of course 1 minus P was 3 over 4. So basically in the previous example, what I just computed by counting those outcomes with 2 heads and 1 tail can be computed directly with this formula by computing B of 3 comma 2 semicolon 1 over 4. 2 successes out of 3 trials. So that's going to be combination of 3 choose 2, 1 over 4 to the power K, which is 2, 1 minus 1 over 4 to the power N minus K, which is 3 minus 2. You can just write 1, but I just want to follow step by step how the formula works. Okay, let's remember the formula for the combination. That's 3 factorial over 2 factorial, 3 minus 2 factorial, which is 1 factorial. 1 over 4 to the power 2. 1 minus 1 over 4 is 3 over 4 to the power 1. 3 factorial is 6 over 2. On the top here, I'm going to have 1 times 3. And on the bottom, 4 to the power 3 combined, right? And so that's going to be, let's simplify this 2. That's going to be 9 over 64, which you remember from the previous example. Which I think I didn't compute it on the previous example. But anyway, I mean, I left it without simplification. But it was, if you look at the previous page, it was 9 over 64. 3 times 3 on the top. Okay, so here's another example, one in which you probably have to use the calculator. So some homework problems will give you already the binomial, the probability of the Bernoulli trials to compute. All you have to do is to follow the formula. So let's say B of 12, or let's say 15, comma 8, semicolon 0.8. So that means 8 successes out of n trials, and the probability of success is 0.8. So that's combination of 15, choose 8, 0.8 to the power 8 times 1 minus 0.8, which is 0.2 to the power n minus k. 15 minus 8, that's going to be 7. 15 factorial, 8 factorial, 15 minus 8 is 7 factorial, 0.8 to the power 8, 0.2 to the power 7. Let's see. Let's simplify this a little bit. You have to use the calculator, obviously. So I'm going to have on the top 9, 10, 11, 12, 13, 14, 15, 7 factorial. That's kind of an ugly problem, actually. But you can put it in the Wolfram Alpha in check or on your own calculator. So this should be approximately equal to, let's see, I have it here, 0.01382. In some applications, as I'll show you later, you may have to use a summation. In fact, I'm gonna show you on the second page immediately when you have to actually do a summation of these type of Bernoulli trials. We'll get to that example immediately, but let's put another quick example on this page. So let's say I want to find the probability of n successes in 12 trials if the probability for success is 0.8, just like before. So again, that's another direct or nearly direct application of the formula. You just have to make sure you write the numbers in the proper position, right? So 12 trials, that means n is 12. So b of 12, comma n, k is 9, semicolon, the probability of success is 0.8. Combination 12, choose 9, 0.8 to the power 9, 1 minus 0.8, that's 0.2, 12 minus 9, which is 3. So let's write the factorials for the combination. 12 factorial, 9 factorial, 3 factorial, 12 minus 9, 0.8 to the power 9, 0.2 to the power 3. Try to do this simplification on your own. Simplify these factorials a little bit. Maybe use the calculator, obviously, at the end. And then this should be approximately 0.2362. Without combinations, this will be very difficult to compute. And obviously, you have to use the calculator because, I mean, you can't be expected to multiply 0.89 times by hand. But you still have to simplify the factorials a little bit to make it easy, even with the calculator. So I'm going to go over 2 more problems on the second page, and then we'll call it a day. So stay tuned. Okay, so take your time to write this down, and while you do that, or after you do that, just pause the video to write it down, but after that, pay attention to what I'm saying here, because again, I suppose this should be obvious by now. What's difficult in applied math in general, or when we try to solve real life problems using math tools, the hard part often is actually recognizing which tools we need to use. So in our case, in this chapter with the probability, the hard part is often to actually recognize whether we need a specific formula, in this case, the Bernoulli trial. Because the formula, I mean, the problem will not say, hey, this can be done with the Bernoulli trial. Why don't you plug in this number there and this number over there? I think that's one of the biggest issues, in fact, with learning math. You need to be able to not just do the computation, but to make the connection between the real life situation and the tool that you have to use. Why what we see here is leading to Bernoulli trials. So let's read the problem. It says that in the country, 23% of the unexpected deaths are due to heart attacks. What is the probability that 4 of the next 10 unexpected deaths reported are due to heart attacks? So one of the key words that this may lead to Bernoulli trials is the question of the probability of a number of times a certain outcome happens out of several instances of running the same experiment. I'm putting here experiment under air quotation marks, right? Because the experiment here is essentially the unexpected death, okay? That is going to be a random event, and the problem forces you to essentially associate two outcomes to this random event. So let's write it here. So the unexpected death is the random event, and of course there are many ways to actually associate outcomes to this random event. You could have more than one disease for that matter, but in this specific question you're looking at actually two outcomes, either a heart attack or not a heart attack. So all other causes are lumped together in the same outcome. So I know that sounds strange, but the way the problem is formulated, this is what constitutes success. I know it's kind of dark, because we're asking for the probability of a number of heart attacks in a certain number of unexpected deaths. But in the language of the Bernoulli trials, this is the event or the outcome called success. Now, what is the probability of success of the heart attack? Well, because we know from the data that 23% of these unexpected deaths seems to be from heart attacks, then the probability of a heart attack in an unexpected death is 0.23. And obviously all other causes are lumped together into the other outcome. They have to add up to 1, so 1 minus p in this case will be 0.77. Okay, so I hope it's clear how this can be recognized as a Bernoulli trial. Okay, so one experiment of some sort that has two possible outcomes, and we ask typically how many times one specific outcome happens if the experiment is run multiple times. So once this is clear, then setting up the question or the answer should be pretty straightforward. So n in the formula is 10, k in the formula is 4, p, like I said, is 0.23, 1 minus p is 0.77. And then the Bernoulli trial formula, that's going to be p, b of 10, comma 4, semicolon 0.23. That's going to be combination of 10, choose 4, 0.23 to the power 4, and then 0.77 to the power 10 minus 4, right, which is 6. 10 factorial, 4 factorial, 6 factorial. At some point, you're going to have to use the calculator. Remember to simplify the exponentials that are bigger, closer together. 7, 8, 9, and 10 over 1 times 2 times 3 times 4. By the way, in some applications, in some exam problems, I may only ask you to set up the binomial, the Bernoulli, that's also called the binomial probability. So to set up this formula like that and not compute the final answer. So if I say just set up the formula for the Bernoulli trial probability and that's it, then you don't have to finish it up. But anyway, using the calculator, this should be approximately equal to 0.1225. Right, so that's the probability of 4 heart attacks out of 10 unexpected deaths. So another last example that is quite important, because you could also have questions like this, may lead to a summation of these type of Bernoulli trials probabilities. And we're going to go back to the coin toss example. So let's say a fair coin this time. A fair coin is tossed 8 times. What is the probability of obtaining pay attention here, at least 5 tails. Right? You shouldn't rush to read these problems because, in particular, make sure you remember that the formula for the Bernoulli trial gives you the probability of exactly k successes. Not at least, not no more, not, so that's a kind of like a different question, right? I mean, it can be answered, of course, with the Bernoulli trials, but the question is, I want to obtain at least 5 tails. Okay, and the formula gives me the formula for exactly k successes. So how do I do this? Well, you have to look at how many times the experiment is run, and basically, again, split the event you're looking for, at least 5 tails, into all mutually exclusive possibilities. In how many ways can you obtain at least 5 tails if you toss the coin 8 times? Well, you can obtain exactly 5 tails, or exactly 6 tails, or exactly 7 tails, or exactly 8 tails. So these are all mutually exclusive, which means when we compute the probability of at least 5 tails, we simply have to add the probabilities of each of these mutually exclusive events. Remember, the probability of union of mutually exclusive events is the sum of the probabilities. So now I can use the Bernoulli trials formula. Because the coin is fair, the probability of success is 1 over 2. 1 minus p is 1 over 2, right? So tail heads. So therefore, the probability of exactly 5 tails is going to be b of 8 comma 5, 1 over 2, right? So 5 successes out of 8 trials, plus b of 8 comma 6, 1 over 2, plus b 8 comma 7, 1 over 2, and then finally b 8 comma 8, 1 over 2. So you need to add 8 Bernoulli trials probabilities, which of course it's going to be kind of tedious, and you have to do this with Wolfram Alpha or with the calculator. Probably Wolfram Alpha is even better. You just write all the factorials and everything, and it should compute it in a couple of seconds. I'm going to just write down the formula, the factorials, and for each of them, and then run the calculator and then see if you get the right answer. So combination, let's do directly, right? Combination 8, choose 5, that's 8 factorial, 5 factorial, 3 factorial, 1 over 2 to the power 5, 1 over 2 to the power 8 minus 5, which is 3, 8 factorial, 6 factorial, 2 factorial, 1 over 2 to the 6, 1 over 2 to the 2, 8 factorial, 7 factorial, 1 factorial, 1 over 2 to the 7, 1 over 2 to the first. So remember, the exponents always add up to the number of trials, right? K n minus k. So 5, 8 minus 3, 6, 8 minus 2, 7, 8 minus 7. And finally, the last one, 8 factorial over 8 factorial, 0 factorial, 1 over 2 to the power 8, 1 over 2 to the power 0. I put that 1 over 2 to the power 0, which is actually 1, just for convenience, so you can follow up with the formulas. In the case of Bernoulli trials, in which the probabilities are the same, so when you have 50-50 between failure or success, this 1 over 2, I mean the p1 minus p are the same, so you could always combine these powers into a single one. That's only when you have p equals 1/2, 1 minus p equals 1/2. So you can make it even shorter and pull out 1 over 2 to the power 8, right? So each of them is 1 over 2 to the power 8 if you combine the powers. and then just put the factorials together here. That's actually, it's not mandatory. I just want to point out that if the probabilities are 50-50 between the two outcomes, you could actually pull out 1 over 2 to the power n, or 8 in this case. So use the calculator and check to see if you get this approximately equal to 0.3633. All right, so that concludes chapter 8. We're going to finish the course with some topics on Markov chains and game theorem. We're going to go back to some matrices and operations of matrices. We still deal with a little bit of probability, but with the tool of matrices on top of that, basically. So specific questions addressed by what we call Markov chains. And like I said, we're going to finish with, I hope, interesting and fun topic, game theory, which is also, which makes use of the matrices as well. So I'll see you next time.